All right, today we're diving into something that is a genuine milestone in AI. It's called DINOv3. This is a new model from Meta AI that's basically teaching computers to see the world, well, less like a machine and a whole lot more like we do. So let's break down how it works and maybe more importantly, why this is such a huge deal.
But to really wrap our heads around why DINOv3 is such a breakthrough, we've got to start with a really basic question. How on earth do you teach a computer to see anything at all?
I mean, think about it. You and I, we learn to see just by, well, living, by looking around. But for decades, we've taught AI using a method called supervised learning. And you can picture this as just force-feeding a computer millions upon millions of digital flashcards. Where a person has to sit there and painstakingly label every single one. This is a cat, this is a car, this is a specific kind of pine tree.
And right there, that's the problem. That whole process, data annotation, creates this enormous bottleneck. Manually labeling the billions of images you need to train a modern AI, it's incredibly slow, it's super expensive, and it just does not scale.
Okay, so this is where a completely different and frankly revolutionary approach comes into play. Self-Supervised Learning, or SSL. The big idea here is to just let the AI learn from raw, unlabeled images, the trillions of photos just floating around the internet, by giving it a clever kind of game to play.
And one of the most powerful versions of this game is called Mask and Predict. The idea is actually pretty simple. You show the AI a picture, but you digitally cut out a piece of it, kind of like a jigsaw puzzle with a missing piece. And the AI's only job is to guess what goes in that blank space. Now, by doing this billions of times, it starts to teach itself the fundamental rules of our visual world. What a cat's ear looks like next to its face, or how a sidewalk connects to a building, all without a single human label. It's learning by context. And let me tell you, this technique worked incredibly well. Models like DINOv3's predecessor, DINOv2, were a massive success. They proved that an AI could learn these really powerful general visual skills just by sifting through these giant, messy piles of uncurated data from the web.
So the path forward seems pretty obvious, doesn't it? Just get a bigger model, feed it even more data, let it train for longer, and bam, you get a super intelligent vision AI. Simple. Well, not quite. As the researchers at Meta AI started to scale everything up, they slammed right into this totally unexpected and honestly pretty frustrating paradox. Training the model for longer was actually making it worse at certain things.
And this is the absolute key. As the model trained for longer, it got better at understanding the big picture, what the researchers call global tasks, like classifying the whole image. But, and this is the crazy part, its ability to handle dense tasks, things that require super fine-grained detail, like figuring out the exact pixel-perfect outline of a person, that started to get worse. The researchers' own words from the paper put it perfectly. They said, as training went on, the similarity maps become noisier. Now, in plain English, that means the AI's understanding of all the little details was literally getting blurry. It was starting to forget how to see the trees for the forest.
So, to solve this paradox, the team came up with this brilliant and actually surprisingly elegant solution. They called it gram anchoring.
Okay, let's not get lost in the math here, but think of a gram matrix as a kind of relationship map for an image. It's like a unique fingerprint that captures all the rich, fine-grained connections between all the different parts. The textures, the patterns, all those tiny little details and how they relate to each other.
So the gram anchoring process is just ingenious. What they do is they essentially take a snapshot of the model really early in its training, back when its vision for details is still perfectly sharp. They save this sharp detail map. Then, as the main model keeps on training and getting smarter at big picture ideas, they use this saved map as a constant guide, like a North Star, to keep reminding it, hey, don't forget about the small stuff.
This technique literally anchors the model to its earlier, sharper self, and it effectively repairs those noisy, blurry features that were starting to creep in. It gives them the best of both worlds, a model that can understand the big picture and sees every last pixel with perfect clarity.
So, the million-dollar question. Did it actually work? Well, let's take a look at the results and see how this new approach actually performs out in the wild. Okay, so this table shows us how DINOv3 stacks up on these dense tasks, the jobs that need that pixel-perfect detail. Now just look at the ADE20K column. That's a really tough test of how well the AI can outline every single object in a really complex scene. DINOv3 hits a 55.9. That is a massive leap over the 49.5 from its predecessor DINOv2, and it just blows the competition away. A higher score means a much sharper, way more accurate understanding.
And this chart really shows off its strength in understanding 3D space. This test basically asks the AI to look at an object, then look at it again from a different angle, and match up the exact same points. This is absolutely crucial for things like robotics. And as you can see, DINOv3 is just in a league of its own, correctly matching points over 64% of the time. It leaves the other models way, way behind.
And here it is, the headline number, 63.0. On that same super difficult scene outlining test, 80/20K, DINOv3 sets a brand new state-of-the-art score. But you know what's truly remarkable here? It's how it did it. Its main vision component was completely frozen. They didn't retrain it for this specific task at all, which just proves how incredibly powerful its out-of-the-box understanding really is.
But you know, it's not just about the numbers. When you actually look at the visualizations of what the model is seeing on the inside, the difference is like night and day. DINOv3's internal map of an image is just so much sharper, cleaner, and it just makes sense. All that noise and blurriness that plagued the older models, it's just gone.
Okay, so the model is clearly incredibly powerful. But what does this actually mean for the future of AI and, for us?
Look, the impact here is absolutely huge. DINOv3 isn't just a single model for a single task, it's designed to be a universal foundation for computer vision. This means you can take the exact same model right off the shelf without any expense of retraining and apply it to this incredible range of problems. We're talking robotics, 3D mapping, analyzing medical scans, even satellite imagery, and get state-of-the-art results.
And this incredible power isn't just locked away in some giant, energy-guzzling supermodel. The researchers figured out how to distill the knowledge from their massive 7 billion parameter model down into smaller, much more efficient versions. And as this chart shows, these smaller models keep about 98.5% of the performance of their giant teacher. This is what makes the technology accessible for all sorts of real-world applications, even on smaller devices.
So let's bring this all the way back to where we started. Remember those labeled flashcards? That was the old way. DINOv3 represents this massive leap forward into a new world, a new paradigm, where computers can finally start to learn to see the world on their own, simply by observing it, just like we do.
And that brings us to a final, really fascinating question. As these powerful new AI models learn to see and perceive the world with a nuance and detail that's completely different from our own, what new patterns, what new insights, what new discoveries will they show us that we have never been able to see for ourselves?